So welcome all to GPU communications and other MPI topics. Thank you for joining us today, and thank you, Dr. Ludovic Capelli, for teaching this session today. He's on his 4th class with us, so he's hanging in there. And thank you, Pascal, for setting up the resources and providing support. Before we get started, I'd like to acknowledge the traditional custodians and owners of the land on which Pawsey is sitting. That's the Whadjuk people of the Noongar Nation. And I'd like to extend that acknowledgement respect to Aboriginal and Torres Strait Islanders joining us today on the call around Australia, and to First Nations people around the world. With that, I will hand it over to you, Ludovic.
Thank you. So, yes, as you've seen, we were trying to the very last minute to get some fancy GPU to GPU hardware to work. It works for Pascal, but not for me, so we'll see how to deal with it. But don't worry, that's for a few minutes. For now, we're going to talk indeed about GPU to GPU communications and other MPI topics, which can be seen as an intermediate level MPI series of topics and concepts. It should connect nicely to what we've seen this morning if you work out this morning. Before we begin, as always, the acknowledgement to the contributors. In this case, there's no one else. I built my presentation on, so it's blazing new path for this one. And the licenses this morning, the note that I designed this slides to be rather light. So we can get straight into the classic moment of truth, and I've seen that some of you already tried it. So you can log on your AWS node. You can reuse this morning credentials. It works perfectly. If you have any problem, especially online, make sure you don't hesitate to say it in the room. You also want them to say it. But online, it's make sure that if you have any problem, you write it in the chat and or unmute yourself to ask questions or raise any concerns so we can know about it. The only thing is really make sure you don't stay stuck in silence. Once you're connected to your AWS node, you can then clone the GitHub repository. And normally, everything should work for you. So let's try to do that. Once you have logged on your AWS node and successfully cloned the GitHub repository, please drop a little thumbs up in the chat so that we can see that everything goes well. And if it doesn't go well, please say it in the chat as well. Get in it. You will see that you have 2 folders available, C and F, standing for the C programming version, and the Fortran programming version of the exercises. They are both provided. Not for all exercises, I'll come back on this in a minute, but still. Get in the first folder, the preamble, try to make it, and to run it, not using that, using MPI run -n something. Is there anyone who doesn't know how to run an MPI program on Teams? If needed, I can easily show the MPI run command here. If you were here this morning, you have done this a few times now. If you are not, it's fine. It's intermediate MPI, so it's very likely you already know MPI. But in case if you're stuck, say that will become the 4101. Okay, I should do it right now. So we're going to start talking straight away about something called GPU to GPU communications. So if we start with the basics again. When we talk about GPU programming, we have the host and have the device, typically the host being the CPU and the device within the GPU. These don't have the same memory space. Okay? They have different memory spaces, which means one address on the CPU does not access an element on the GPU and vice versa. So since they cannot share memory directly, we're going to keep the unified model away from now. Okay, we're going to stick to a good old architecture where there's no memory share between the two. They need to be transferred. All data needs to be transferred. Sometimes we have to pin the memory, because by default, when you allocate memory, it's what's called pageable memory. Right? Is it the right time? Pageable memory? Yeah, okay. where the OS can freely move the memory around the page on which you're currently located. If you're pinned, without going into much detail, that address will remain where it is. It allows the GPU to predict where the CPU counterpart is. Anyway, the key point is this: transfer is slow. Inside the GPU it's really, really fast, but moving data from the GPU to the host, to the CPU, the host system, that is much slower. By a factor of easily 100. Yeah, nearly 100. So unified memory model, yeah, is the new architecture that allows the CPU and the GPU to actually share memory directly. So there's no transfer needed because they already share that in hardware. But we keep the other side on that. This is how we normally pass data through MPI, because we're still talking about MPI programs here, right? So when you want to send data, normally you have first to bubble up your data from the GPU to the host. So then you can have a nice CPU pointer to the data held on the host before sending it to another MPI process, which will receive it on the host side and potentially then ultimately transfer it again to the GPU. Okay, so GPU back to host in the MPI process to another MPI process, and then it gets back to the GPU. And that's how you can do it in Fortran, but same thing here. Now, as hardware evolved, more features became available. We're taking CUDA here as an example because this is what you have available in your AWS, but it's the same with HIP. The optimization, the technology behind the scenes, though not identical, still provides the same features. The first one we've seen was in CUDA 3.1 with the GPUDirect, where the host and I think it was the network fabric, yes, the host and the network fabric could transfer directly data between the two if it was a pinned buffer. So that allows to remove certain copies. Now, the one that was really interesting is the one that came next in CUDA 4, which is called the GPUDirect P2P. This one allows data to move from one GPU to another GPU without going through that slow host device. And the one that came after the GPUDirectRDMA is the same, but with GPUs on different nodes. So let's take a step-by-step approach. We are considering an intra-node setup. Okay, so we have one node, and we're just considering a node with, for example, two GPUs. A GPU A and a GPU B. We allocated a buffer, okay, in our program, MPI or no MPI. And the thing is, for GPUs to communicate with the hosts, they must use a pinned buffer. Either you do it yourself, or you just ask for a classic malloc array, but behind the scenes, there will be another buffer pinned, allocated. You won't see it, but it will be there. If I want to move data from this GPU to that GPU there, you will have the slides. By the way, if you were not here this morning, you have the slides that have been given to you, so you can follow the slides if you can't see on that. First, I need to transfer the data from the GPU to the host using this pinned buffer. Okay, that's the first step. Once I have the data in my pinned buffer, I need to move it in my buffer that I actually allocated before transferring it to the second pinned buffer, the one for the other GPU, before it gets transferred to the final GPU. Okay? So that's two transfers, two copies, to move from one GPU to the other. If we start again, this time using GPUDirect peer-to-peer, we can move from the GPU1 to GPU2 in one go. So we save we transfer in two copies. So all this in between goes away. We don't even go through. So all in blue, you can see the devices. In red, you can see the host. So you can see that GPUDirect, the peer-to-peer, allows to bypass entirely the host. That's why it's named GPU-to-GPU. We don't go through the host anymore. Of course, it requires special hardware behind the scenes to link GPUs, but we always project ourselves in these examples as having this type of hardware. Now, let's try to look at what it looks like if we are on an inter-node setup, so multiple nodes. Now it's much worse because we have to bring GPU data back to the host end, like we did. Then we have to move from the pin to the host buffer, just like we did before. But now we also have to go through the network, which means we have a network adapter to go through. So we must copy again from the host buffer to the network adapter buffer and all the way back. So that's 2 transfers, 4 copies to move data from a GPU to the other GPU. Again, on different nodes. The first GPUDirect, which allows pin buffers on the host and on the network adapter to move from one to another without going through the intermediate buffer, allows it to move from this to there. So it saved us 2 copies already. The whole GPU-to-GPU thing is about removing intermediate copies. It's only about that. Because we know that when we get out of the GPU, it's slow, so we try to not get out of the GPU, or as little as possible. And with the other variant, the RDMA, what it allows us to do is to go directly from the GPU to the network adapter and have that sent to the other GPU. So we bypass everything in between and can move between a GPU to the other GPU in one go with a network adapter in between. But we still have to look at it. So yeah, that's what the technology allowed us to do, which is very interesting. That requires, of course, a GPU-aware MPI implementation. But assuming all this is set up, there's nothing much to do in your code. There's still a few things to do or to stop doing. I'm not talking about the actual setup, but really the source code itself, because there is something you no longer need to do, which I'm going to show in a second. But yes, that's one of the nice things of GPU-to-GPU. It's very hard to get it right. That's why we're still with Pascal. We're still like trying to get that right. And it seems it works for Pascal, but it doesn't work for me. I don't know why. But at least it works for someone. I'm happy, so we can have someone to show. And even if it doesn't work on my screen when I show it, I can still say, well, look at Pascal's. It works. So yeah, so I'm staying quite on the surface here of GPU-to-GPU communications because it's hard to really go deeper. It's hard to go deeper without going deeper in the actual GPU programming side of things. So in CUDA or HEP or OpenACL or OpenACC or something else. So since we're trying to keep it focused on the MPI aspect of things, I won't go into too much details here. Instead, I will show you the code, which is the code in the exercise 2, where since it's not working, you don't have to do that as an exercise, okay? But yeah, as I was mentioning before, quickly going to the exercise, as I was mentioning, there's a lot more to learn about GPUs and GPUs in general. They have really become a core part of HPC. GPUs are just very powerful devices, and learning how to use them. Well, they don't have to prove their value, right? Well, we just know they're very valuable. They're not sufficient in themselves. We still need the CPUs, but they're very, very powerful devices. So whether it's an NVIDIA team or AMD team, don't worry, both of them have you covered. You will have GPU optimization techniques available, especially since the most recent I mentioned was in CUDA 5, and I think by now we are at CUDA 11. Or the GPU capabilities can go as high as 11. So 5 was quite a few years ago now. I think 2013 to that list. So anyway, this exercise here you will not do. I will show instead. Unless,
I'm typing just the commands that can try, which on the walls, if you log in your node, everybody should see the broadcast of what they can try to do.
So you're seeing the errors in the chat.
I put it actually straight on the node, so everybody who's on the node sees just like they can copy things.
Oh, okay. Because there were one from Lorenzo and one from Henry.
Put it here, it's fine. So here is an example of a program that has an output that's in common here now. Oh, sorry, I will uncomment this and I will comment that instead. Okay. I will do this one here and comment this. Okay. If I try to compare this. That's nice. Okay, well. Oh, we're back to the other one. We have to
Go back into add the. I think it's just your log. You try to go back. Extern C. Extern C.
Oh, it's clean. Okay. No, it's in the increments.
That should be fine.
It complains.
Yeah. So now you find a reference to launch increments.
Maybe speak the logic that you're thinking through for individuals on the call.
Sorry?
Yeah, just so that we can learn from how you're troubleshooting on the call. So if you're thinking through if you're talking through your thinking.
Yeah, well, so as soon as you see your program undefined reference, it means there's something missing at lane time. So if
you go back to your GPU to GPU.
I'll do that first. Yeah, that's the one.
Okay.
That's recompile. Because we've been changing. Well, we know Pascal. Pascal went through the efforts to update the wrappers, the MPI wrappers, the NVIDIA compiler, and everything. So sometimes some of the code I compiled was compiled using a different compiler. So then when you try to link, there's an error coming. So now just run. Normally I still have the environment variable set up. Okay, so what we see so far in this code is here. So I allocate some array. Okay, if you're not familiar with CUDA, we'll go through that together. So I have an array of 10 elements, okay, 10 integers, very classic here, which I initialize to 0, 1, 2, 3, 4, 5, 6, and so on. Now, I know that this is only available on the host, i.e. the CPU. If I want to have also that on the GPU, first I need to allocate the data on the GPU, which in CUDA you do by calling CUDA malloc. You see, they are not far. Malloc is the C dynamic allocator, and in CUDA it's just CUDA malloc, so very same thing. I want to allocate size in bytes, so 10 times the size of an integer. Okay, so let's say 40 bytes. Typically, an integer is 4 bytes these days. So yeah, 40 bytes. And the pointer on that memory on the GPU, not on the CPU, on the GPU, will be contained in this pointer here, array device. Okay, so array host is available on the CPU, array device is available on the GPU. So now, what I do is, I have my array on the CPU that's set up and initialized. I need to transfer this data to the GPU so that it's there too. So this is this memory copy here. Okay, so it moves from array host to array device using a CUDA copy host to device. This parameter here indicates in which direction data flows. So host to device in this case. Then I have this CUDA kernel behind the scenes, which does not much. It just increments every, here. It just launches a kernel increment, which I created here, which just increments every element in the array by 1. Okay? I won't go through the actual CUDA part of block IDs, block index, block div, and so on, or this notation of grid size, block size. This is CUDA programming, so that's a totally different topic. But just believe me that when I say it increments every element in the array on the GPU. So once we call that, on the GPU, every element in this array has been incremented by 1. So now, on the GPU and the CPU, we no longer have the same values. The values on the CPU are now out of date. So we need to bring the data back to the CPU with another CUDA mem copy, which, again, remember, will go through that pin buffer behind the scenes that we don't see and so on. Once we're back with the data on the host side, that I can send with MPI send. Okay, very simple MPI send here. Up. And it means that on the recipient, they can receive that in their own buffer. They can put that on the GPU if they want, again, by moving the data to the GPU, and launch the kernel again, so to increment again everything, and then bringing everything back to the host before printing it. Which, by the way, it still showed 0, 1, and so on, right?
Yeah, so I'm just thinking it's the launch kernel, but it's not doing something.
I think it just doesn't detect GPUs.
Can you check CUDA visible devices?
So
that one should be defined, but if you do ROCm NVIDIA, can you do NVIDIA SMI? For everybody, this would be useful. So NVIDIA SMI reports all the devices it sees. It's dash SMI. It sees, everybody should see 4 GPUs.
I think somehow now we're seated. Oh, see from within the MPI code. Why do I think there's something funny going on? Is because look, it still shows 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it doesn't show incremented values. That's why I think somehow now something funny is happening somewhere.
Looks like Henry can see 4 GPUs with NVIDIA SMI.
Yeah, everybody should. Unless they copied the CUDA visible devices bit to limit their scope.
Yeah.
Everybody should see 4 GPUs.
Okay.
You're going to see always the same GPUs.
See that as well, Stefano?
Yeah.
Yeah. Great.
Okay, so that works. Right.
I can quickly
Well, if I will get the same output with a GPU aware.
exactly.
Anyway,
so
so
you're getting the right answer.
sorry.
You're getting the GPU aware working. You're not getting kernel launch working, which I don't understand at all.
So in this case, we'll just project ourselves in a situation where you have to trust me.
I can briefly share my code, but I make a screen. But people should try because they should see 2, 3, 4, 5, 6.
And the fun thing is,
I'll say 0, 1, 2, 3.
Okay.
sorry.
Mine's not working, so I'll say 0, 1, 2, 3.
Okay. Well, for the record, this was working yesterday evening. So it's just a matter of getting the right software stack, which is, I must say that when we were discussing with Cetonix incident and okay, what would be the plan B? And Pascal got the AWS. I thought, wow, the challenge is going to be the software stack working for the GPU with MPI and everything, because I know that this is a nightmare to get going. It's like in HPC, this is really the hardest part. It's not programming. It's when you have to set everything up, the libraries, the compatibilities and everything. So that's really, really, really hard. Anyway, so what happens here is the important bit, regardless of the output, trust me that this program is correct. Somehow there's something going funny somewhere, but the program is correct. The important bit here is I had to bring the data back from the GPU to the CPU. Now, if we are in a position where we have this GPU-aware MPI, it means I can save this CUDA mem copy here. I no longer have, once I have the updated values on the GPU, I no longer need to bring them back to the host and send a host pointer. Instead, I can just send, and that's really the useful part, I can just send the device pointer here, see? Here I was sending array host, and here I send array device, which means I can send directly a GPU pointer through MPI, because MPI is aware that this is a GPU pointer and it will treat it slightly differently. For example, you were here this morning about bsend. If behind the scenes the MPI send issues an MPI bsend, it will not try to copy it into a buffer if it knows it's a GPU buffer. That's what GPU MPI means. GPU aware MPI means. It's that it won't do these kind of things if it knows it's a GPU. If it doesn't know, that's simple, the whole thing will crash. If you have a GPU unaware MPI and you try to do this, it will just crash. Because here, same thing, you don't receive in a buffer on the host, you receive directly on the GPU. So let's try to make this again the you're gonna have an idea. Where am I here? Okay. No, it's the right one. Okay. I thought maybe I was not editing the right file or something, but no. Okay. Well, again, not the right output. Something funny happened somewhere, but don't worry. If it was not GPU aware, it would just crash. And I can tell you because I tried that also yesterday. So yeah, normally it's not GPU aware, it crashes. So again, this might seem a bit weird because we're not using additional MPI routines, we're not using additional MPI concepts or anything. We're just removing lines because normally we have to bring the data back to the host, and this time we don't. But that's actually the full value of these GPU communications. Any question? Given how tricky that can be, plus the Pascal does it. So it means he has an idea. Go ahead. What was the idea?
I think it didn't auto-propagate adding video to. So there's a special video group that you have to be added to launch kernels on the GPUs. It didn't add that automatically, and I thought it did. So I think that everybody's not in that group, and so you can do all the GPU MPI. You can do everything with GPUs. You just can't do a kernel on the GPU. Because there's a permission issue. So I'm going to add everybody to the video group, and then you can try this in a second.
So in the meantime, there's a question
Yes.
from Lorenzo. Is there a way to know whether I have a GPU aware or not? A
Yes.
priori, maybe based on the GPU version or a command?
So that's the trick here. Well, the easy way to check if it's GPU unaware is to run the program that you currently have, the one that is uncorrect, the one currently I showed, right? Because if it's not GPU aware, it will crash. Why? Because MPI is receiving a GPU pointer, but it has absolutely no clue that it's a different pointer than the host pointer. So it will try to treat it like a CPU pointer. So it will try somehow to dereference it, but it will end up somewhere totally unexpected in memory, because remember, a GPU pointer is still a pointer. So it's just a variable with an address in it. But this address is not on the CPU memory space, it's on the GPU memory space. So whatever address is in it means nothing on the CPU side of things. So if MPI receives this pointer and is not aware that there's such a thing as GPU pointer, it will automatically think it's a CPU pointer. So if I want to send the data over the network, I know where to get the data. I will just go to the CPU side of things and I will go at this address. But the address of the GPU means nothing, so it will try to access an address that it's not allowed to access, which is a segmentation fault. You're accessing a memory segment you're not allowed to. The operating system sees this, says segmentation fault, and crashes the whole application. So that's a quite brutal but efficient way to check that you don't have a GPU version. Now, when it comes to the GPU, because the question seems simple, but the answer is in, I think, 3 levels. So the first part is when we can check this one. Now the GPU, the capability, yes. Since the GPUDirect techniques have been created in CUDA 3.1, 4.0, and 5.0, if you have a GPU whose CUDA capability is 2, you know you cannot have the support for this. If it's 4, you know you'll have the support for the first 2 techniques, but not the one between nodes. So there's that aspect. Now, even if you have the CUDA capability, you need the actual architecture behind the scenes, the NVLink and everything. And even if you have all this architecture, as we've seen recently, you can still not be able to use it because it's very hard to get everything set up. Normally, when you go to HPC, don't worry, all the supercomputers, people like Pascal already had headaches making it work. So when you arrive, it's all working for you, and we're very happy users. That's I'm having the easy job in life. I'm just a user. So I come with my programs and I say, oh, I want to run it, and it works. If it doesn't, I can't debug it. That's not my area of knowledge. This is why if you want to become an HPC system administrator, typically they're well paid because it's very hard to do. So yes, so that's one way to check it.
I mean, it also has to be hardware. So some things will not have the hardware available to do RDMA, and that you have to look up the hardware and be like, oh, my network gate is not able to do this. And that's typically what happens on cloud computing. You get some cloud computers. Typically, that's the more expensive bit, so they just usually provide a GPU with no GPUDirectRDMA capability. So if you've got a bunch of things, you have to go the old-fashioned way and just send data slowly.
Yeah. Again, it's not again. What do I say again? I often start by saying again, but there's no transition. I would say that GPU to GPU communications, because you need to understand where you might need it. It's when data on a GPU is needed somewhere else on another GPU. That's not as frequent as this. Typically, what we put on a GPU is rather an isolated piece of computation. However, yes, sometimes you will have some data like neighbor halos or neighboring dependencies where you would need to swap columns in a 2D array you're processing or something. And then, yes, your GPU to GPU communications could become very handy. Because your problem is not really even the bandwidth, because you're unlikely to move gigabytes of data from a GPU to the next. You're likely to exchange a few dozen, 100 bytes, which means nothing. But the latency, all the copies, these latencies just stack up, and it means that it can become a problem. But depends, of course, on how much time you actually spend computing. When you're on the GPU, expectedly, you're in a position where you have a lot of computation to do. So you're not doing half a millisecond of computation and then you need to move the data out. Otherwise, it's unlikely you would find that putting that on the GPU would be helpful in the first place. Normally, you're in a position where what you put on the GPU keeps the GPU busy for a while. And once you're done, there's some result to extract and maybe exchange. Does it make sense? Yes, online. Remember, online I have absolutely no feedback loop from you, so I need you to have the little thumbs up and everything, so we can see it. And I don't even have the videos either, so I don't know if you are now pulling your hair because what I'm saying makes no sense, or if you're happy or playing a PlayStation 5. Because last time I said Xbox, so I need to be fair. Or Nintendo. Nobody's complaining in the chat?
Nope. So I think that was great.
Yeah.
Yes, all good.
Okay.
All good in the chat.
So that was for the GPU part of that talk. It seems a bit isolated, but at the same time does the link between the OpenMP GPU you have seen, the MPI, the fact that in MPI you can have some GPU considerations resurfacing, and the fact that now, I was very surprised to discover that the first time that GPUs on different nodes can communicate between them directly. But if you have a look at it, that's exactly how peer-to-peer, that's why one of the optimizations is called GPUDirect Peer-to-Peer. That's how peer-to-peer worked, and that's why it became so powerful. It's when you are downloading a movie, legally, peer-to-peer, but legally still, because it was a movie without copyrights, so in the public domain, which you're allowed to download it. The way it worked and why it revolutionized everything is you were going to the server, you were going to download from the server. But at some point, a new approach was followed where you would go to that server and that server will tell you, okay, if you want to download that movie or that file, that picture, you can get some fragments of it from there and from there and from there. So you were no longer all hitting the same source. You are now having bandwidth shared with different other hosts, becoming a host yourself in the process. So that's the same thing happening with GPUs. It's like a GPU wants to communicate with another GPU. You no longer go to the host. The host just tells you, oh, it wants to go to this GPU, right here. So that's fun. I can't wait to see what other type of extra links we're going to create in the future with components and things like this.